For this next part, we're doing a quick review of some of the past reactions we've had in Chem 1 and 2. This is usually pretty hard for people to remember all the reagents that you've learned up until now. So what I would recommend is try to do this just like that if you can. And let's pause it and give you a chance to try them out. But if you need to, I have some options for things that are part of the answer, and that is right here. These are some of the reagents that you might need. It would be great if you could cover that up or not look at it and still be able to do this problem. But if you're having a really hard time, then maybe look at some of these answer choices and see if you can recognize where they go. All right, let's pause it and give this a try. All right, so I'm going to walk through this with you. We've got, at least the way that I think of these, and maybe it might help a little bit. We've got a 3-carbon chain here, and I'm changing. I like to focus right in on what how is the functional group changing? How is the carbon chain changing? So in this case, carbon chain's not changing. We're just doing an oxidation from an alcohol to an aldehyde. So I need an oxidizing agent, and I recognize those are sitting right here. And I need to choose the right oxidizing agent. I've got primary alcohol going to an aldehyde. I don't want it all the way oxidized to a carboxylic acid. So I don't want the stronger reagents. I don't want the Jones reagent or dichromate or permanganate. I don't want those. They're too strong. They would take this all the way to carboxylic acid. So I will use the more mild pyridinium chlorochromate, which is PCC. So hopefully you recognize that one. All right, for the next one, I'm going to do the same thing. I'm going to highlight what's changing. And you can see it's the same kind of thing, but this time it's with a ketone. Ketone is oxidizing, aldehyde is oxidizing to a ketone. So here it doesn't actually matter what I use because I don't have the choice of an aldehyde and a carboxylic acid. It's just it could only oxidize to a ketone. There's only one choice. So that means I can use any of these. So maybe I'll just use sodium dichromate just for fun, just to have something different. But you could also use PCC here or potassium permanganate. For the next one here, I hope you see the 2 here means that there's 2 of these molecules. So I'm taking a 4-carbon chain and I'm splitting it in half. So that's oxidative cleavage. And I'm ending up with this aldehyde. So I want an oxidative cleavage under reducing conditions, so reductive cleavage. So that means I want to use zinc and water, or DMS is another choice for a workup. So this is ozonolysis followed by reducing conditions like zinc is a reducing agent, or DMS, dimethyl sulfide, is another reducing agent that will keep it at the aldehyde rather than fully oxidized to carboxylic acid. If you want to fully oxidize this to carboxylic acid, you'd have to use the cleavage with hot KMNO4 heat and an acid workup. So just FYI. Here in the next box, we have the similar oxidative cleavage, but we're getting ketones now. That's because there are 4 R groups on this molecule. Here we only had 2. So with this, there's the only option of getting ketones. So just like with this one, either of these oxidative cleavages would work. So for variety, I will use the hot KMNO4 to cleave that. And acid workup is usually for carboxylic acids. If I were to make those, I would want them to stay protonated. All right. But I'll leave that in there. Okay, so now for the next one, I've got an alkyne turning into an aldehyde. And so if you recognize that the less substituted carbon here is the one that's changing, then I want to have Markovnikov or anti-Markovnikov. Well, hopefully you remember less substituted carbon. Addition to that means anti-Markovnikov. So of these 2 reagents, this one's the anti-Markovnikov one. Now we tend to use an alkylated borane, so an alkyl borane rather than just BH3. We use R2BH. But if you see BH3, it means the same. They're talking about the same thing. NaOH, H2O2. This is the hydroboration reaction, hydroboration oxidation for alkynes. And I encourage you to go back and look at these mechanisms as well. These are things that you should keep learning and remembering throughout OChem. All right, for the next one, we have, again, alkyne, but this time the reactivities on the more substituted carbon. So this is the addition of water to an alkyne for more substituted. So this is similar to the alkene reaction. If I had an alkene, I would use H2SO4 and water. Or I would use the oxymercuration reaction, mercuric acetate, THF and water. For the alkynes, we use mercuric sulfate. So I'm going to put that in here, HgSO4 and some acid, H2SO4. That's for the tautomerization of this. When you have an OH group, it's an enol, and then it tautomerizes to the ketone. And that tautomerization is catalyzed by acid. All right, so that's what we have so far. Great. So go back and review your alkene-alkyne reactions. See alkene here and alkyne here. Okay, the last one is an electrophilic addition reaction. We are adding an R group, but it's an acylated R group, meaning it has a double bond O. So we want a Friedel-Crafts acylation rather than an alkylation. So the acylation means that we're going to use this reagent. So I want the R group here with a halogen of some kind, either bromine or chlorine. So that part is easy. And then I need a Lewis acid catalyst to make this into a better electrophile. So this is electrophilic addition from the last part of Chem 262. All right, so hopefully this is just a little sampling of, first off, some reactions from the past. You have alkenes, alkynes, rings, aromatic rings. You have oxidation, maybe review your reductions as well. And these are all reactions that involve making aldehyde or ketone, and that is the subject for today, is aldehydes and ketones. So please go back and review all those reactions from before.